All right, so we're going to look at velocity time graphs today, but here's just something that I've been thinking about recently. I think sums up, what I've been thinking about. So life itself implies control, after all, in individual cells and organisms no less than in national economies or any other purposive system. It's by James Bendiger in a book called The Control Revolution, which I just sort of been flicking through. It's fascinating to think about the fact that at all levels of system sort of perspective, like biologically, psychologically, socially, we're moving towards systems of control because we have to reduce the entropy and reduce disorder. So that's interesting to think about. Anyway, we're going to look at velocity time graphs, and what I'm going to do is I'm just going to let the video play for the most part here, and then I'll come back later and explain it in more detail. But just the first thing to say is what we're going to be doing is analyzing the motion of this point P. So this is down the bottom, you can see the path that this point P is tracing out, and it has a position function, x of t, which is 3 sine t. And then if we were to think about the velocity, this would be the velocity graph. Velocity as a function of time would look like this. And we know as well that the acceleration is given by the gradient of the velocity graph. So that might look something like this. And the displacement is given by the signed area bounded by the graph and the t-axis. So the signed area taking away the positive and negative components. And the distance traveled is given by the total area. So that's really it. I'll go through now and explain each one in a little bit more detail, but if you sort of understood the gist there, then you're all good to go, because that just sort of helps us understand what's going on with these velocity time graphs. I might just go back to here and just explain from the top if you're interested. So yeah, this point P is the thing that's actually moving. So this is the motion of the thing that we're actually analyzing. This x of t is position. So you can sort of see, because this point P is going back and forth, we end up with this sine graph. And I've just made it such that it goes up to 3 and down to -3. So at the moment it's at -3. So it's down in this position here. And then it goes back to the origin there. And then it goes to the point +3 up there somewhere. And then it goes back to 0. And then what we can start to think about is, well, that was moving in that time. So we can start to think about the velocity. Now remember, velocity is a vector. So it's got a magnitude, so it's got speed, and it's got a direction. So if we were to look at that, I think you would agree that basically the velocity is how quickly your position is changing. If you change your position, so if you change where you are quickly, then your velocity must have been higher, for example, right? So if we think about the velocity time graph, that's the derivative of the position graph, and the derivative of 3 sine t, I'm hoping you've done a bit of this before, is 3 cos t. So if we then play that and then try and map these velocities to this point P, you'll hopefully start to see that they map, right? So at the start, actually, let's go to this point here. That point P gets right to the top there, and it goes to 0. The velocity goes to 0, an x-intercept at that point. And then it comes down. When it gets to this point, I encourage you to think about what's going on for that point P, but I think you would agree it's traveling in the negative direction with maximum velocity. So that minimum corresponds to a maximum velocity in the direction towards the left, where the left is considered negative, right? And then back to here, it goes to 0. And then here it's maximum velocity to the right, and then back to 0, and then back to the middle point there. And then, so from there, what we can say is, and if you look at the previous video that we did, some of the information that we can get from the velocity time graph is that the acceleration is given by the gradient. So yeah, acceleration, just like the rate of change of position gives you velocity, the rate of change of velocity gives you acceleration. And that should make a bit of sense. Let's try and sort of map it to this point P in terms of what's going on. Let's look at this point here. The acceleration you can see is -3. So at that point where it just gets right to that point negative, it gets to that point position of 3 to the right, that's when it's being pulled most to the left. So the acceleration is -3 to the left. So it's sort of, there's a force. If you think one of Newton's laws, F equals ma. You can think of acceleration as kind of being like a force that's pulling it towards the left, like an elastic band has stretched it out and it wants to pull it back in the other direction. Okay, let's just let this play through a little bit and see what happens when we get to down here. All right, if you sort of saw what happened there, and maybe I'll let that play a little bit better. Let's do that again. So acceleration is -3. All right, so just at this point here, it's interesting. I encourage you to pause and think what's going on there. Why is the acceleration there 0? And I think you'd agree, if you ever think about it, that that point P is traveling at a constant speed at that point. And when you're traveling at constant speed, there's actually no acceleration. There's no force acting on it, I suppose is one way you could think about it. So the acceleration there goes to 0 right at that point there because it's traveling at constant speed. Okay, and then to here, the acceleration is +3 because it's being pulled most to the right. Remember, these are all vectors, so they have direction. So the acceleration is towards the right now. Acceleration is 0 again because it's traveling at constant speed right in the middle there. And then hopefully you get the picture there a little bit. So I think that's interesting. Okay. The other thing you can tell from a velocity time graph is what's called the displacement. Now remember, displacement is this concept of final position minus initial position. So basically, how far are you from where you started, basically? So if we start at this point P, which is at the origin, the displacement will always tell you how far away you are, positive or negative, from that point. So this is why it's the bounded area. So let's go through and make some sense of it. All right, so the bounded area at the moment is 3, and that should make sense. The displacement is 3 to the right, with the point P has moved 3 to the right. Okay, but then as the motion sort of is sinusoidal, it comes back. The displacement, let me get this right, the displacement there, around that point, I think you get the idea, is 0, right? Because it's gone up to 3 and then it's come back to, it's gone up to 3 and then back 3. So it's now, the displacement is 0. So the bounded area, you've got area above the x-axis, which is +3, and the area below the x-axis, which is -3. And so that cancels out to 0. And then the bounded area becomes -3. And then back to 0, +3, and back to 0. So you can see that, yeah, the bounded area tracks our displacement, which is kind of interesting, right? Just, you know, if you're really interested, each sort of section here is 3. So it has an area of 3. This part here has an area of 3. Interestingly enough, I didn't even really plan for that, but obviously the integral would work out that way. So maybe get a pen and paper out and sort of calculate the integral from, say, 0 to this intercept. But obviously it gives you an area of 3 based on these calculations. Let me know if I've made a mistake there. I think that's right though. Anyway, the last thing to say is really interesting. If we don't take the bounded area, so we're not taking the signed area, if I got that right, we're not taking the plus and negative part, we're just taking the total area now. We can see that the total area that it's traveled is essentially 18, whatever the units are, meters, centimeters. So yeah, you know, 3 meters, you've traveled 3 meters to the right, then you travel 3 meters back to the origin, and then here you go. Oh, let me just play it one more time rather than talk about it. So you can sort of see the total area accumulating. So 3 to the right, so we've gone 6, now we've gone 9, now we've gone 12, 15, 18. So the total area under a velocity time graph will give you the total distance that your point P has traveled. So that's sort of big picture stuff. If you really understand those concepts, though, I think a lot of the problems that you'll be faced with will be a lot easier because you hopefully have a sort of deeper conceptual understanding of what's going on when we analyze the motion of some point. Hopefully you found that interesting. If you did, give us a thumbs up, give us a like, tell your friends. Good luck with all your studies. If you need any private tutoring, get in touch, and hopefully talk to you soon, and happy studies.